Some basic definitions. Periodic function. A function that repeats its value at a regular interval or period is called periodic function. Right function. It will repeat after some time. So if you are taking sine pi, sine curve or cosine curve 0 to 2 pi, after 2 pi it will repeat the same curve, right? That is what it is, periodic. You can take simple pendulum, right? It will go and come back. So bouncing a ball, if you throw a ball it will come back, right? These are all the period, right? Simple pendulum, a rocking chair, right? It will come back and go back, right? Bouncing ball, sine wave, cosine wave, all are, see, sine wave, it is repeated after 0 to 2 pi, it will repeat same style of the curve, right? Now square wave, it will be a square, like square type waves, it will repeat. And the triangular wave, it will be like a triangle, right? Absolute integral over a period function. If a function whose absolute value is integrable over a specific time interval, right, is finite, then it is called absolute integrable function over a period. So for example, the integral of absolute value of f of x, which is equal to e power minus x, over the interval closed interval 0, open interval infinite. The integral of absolute value of f of x, which is equal to e power minus x sin x, over any finite interval. So these are all the absolute value, absolute integral over a period of function. Next, piecewise continuous function. A piecewise continuous function is a function that is continuous on each of its pieces but may have discontinuities at the end points of the pieces. So there are so many pieces in that function, so each pieces it will be continuous, then at the end point of the each pieces it will be discontinuous, right? That is called piecewise continuous function. A piecewise continuous function is made up of different pieces, right? There are so many pieces or subfunctions. Each pieces represent a function, that is called subfunctions, right? Defined on different intervals. Example, f of x is equal to x plus 1 if x is less than or equal to 1, 3 if x is greater than 1, right? See the function. F of x is equal to x plus 1, x is less than or equal to 1, f of x equal to 3, x greater than, there is a discontinuity between them, right? So red dot and white dot, that is the discontinuous, right? But in f of x is equal to x plus 1, it is a straight line, there is no discontinuity. Then f of x is equal to 3, there is no discontinuity, it is a straight line, right? Absolute value function, that is the standard example. F of x is equal to modulus x, x if x is greater than or equal to 0, minus x if x is less than 0. This function is like that, right? If x is equal to minus x, that is a straight line, and f is equal to plus x, it is also a straight line. At the point x is equal to 0, it will be a discontinuous function. The function does not exist when x is equal to 0, right? When f of x is equal to 0, f of x is equal to 0 only, right? The same point, only one point. Piecewise differentiable function. A piecewise differentiable function is a function that is differentiable on each of its pieces. So it will be a, the function will be consisting of so many pieces. In each pieces the function is differentiable, but may not be differentiable at the end point of the pieces, like piecewise continuous, right? There the function is continuous, here the function is differentiable, right? A piecewise differentiable function is made up of different pieces or subfunctions defined on different intervals. Example, the sine function of x is equal to 1 if x is greater than 0, 0 if x is equal to 0, minus 1 if x is less than 0. So second one, So it is differentiable first case. In the second case also, f of x is equal to x square. If x is less than 1, right, you can easily differentiate x square in x less than 1. 2x minus 1, it is also differentiable when x is greater than or equal to 1, right. Bounded variation. The function f from the closed interval a to b to r is said to be bounded variation on the closed interval ab if and only if there is a constant m greater than 0 such that summation I is equal to 1 to n modulus f of xi minus f of xi minus 1, which is less than or equal to m for all partition p, which is equal to x0, x1, etc., etc., xn of ab. So first the given interval, closed interval ab, we are dividing into n small parts, x0, x1, x2, etc., etc., xn. We are applying that function f on that. So the difference between f of x1 and f of x0, right, you are taking, and then take the next summation f of x2 minus f of x1. So you are adding up all the difference, it will be less than or equal to a positive number m. Then the function is bounded variation on the closed interval ab. Or if f is a function from the closed interval ab to r is bounded variation on closed interval ab, then the total variation of f on closed interval ab is defined to be vf of variation of f, that is called v suffix f ab, which is equal to supremum of summation I is equal to 1 to n modulus alpha xi minus alpha xi minus 1, right, such that p, which is equal to the partition x0, x1, x2, xn on ab, right. Example, if f is a function in the closed interval ab to r is monotonically increasing, then for any partition, right, x0, x1, etc., etc., xn of ab, definitely it will be like this, right, summation I is equal to 1 to n f of xi minus f of xi minus 1, which is equal to summation I is equal to 1 to n, because monotonically increasing means f of xi is greater than f of xi minus 1, definitely, right, because f is monotonically increasing, right, like 1, 2, 3 value will be f of x value will be 1, 2, 3, right, like that it will be increasing, right, monotonically increasing. So definitely f of xi minus f of xi minus 1 is a positive number. So we removed the modulus, summation I is equal to 1 to n f of xi minus f of xi minus 1. So summing up, so f of x1 minus f of x0, substituting I is equal to 1, 2, 3, etc., etc. So you will get plus etc., etc., plus f of xn minus f of xn minus 1. So here f of x1 then minus f of x1 get cancelled, f of x2 then minus f of x2 get cancelled. Similarly, f of xn minus 1 and minus f of xn minus 1 get cancelled. So remaining you will get f of xn minus f of x0, right, which is less than or equal to f of b minus f, definitely, because x0, x1, x2 are the partition in the closed interval a comma b. So b is the highest and a is the lowest. So f of b minus f of a, which is a number which is definitely greater than all the difference, f of xn minus f of x0, right. Hence f is bounded variation, and vf of ab, which is less than or equal to f of b minus f of a, it is a number, right, f of b minus f of a. Next you can take the function f from closed interval 1, 5 to r such that f of x is equal to 1 for any partition x0, x1, etc., etc., xn of 1, 5. Definitely you will get, we know the modulus of f of xi minus f of xi minus 1 summation less than or equal to f of b minus f of a. Here f of b means 5, f of 5 minus a means f of 1. So both value are 1, because by the definition of f of x it is 1, f of x is equal to 1 for any partition. So f of 5 minus f of 1 minus 1, which is equal to 0, right. So f is bounded variation, vf of 1, 5, which is less than or equal to 0. Next, Dirichlet's condition. A function f of x satisfies Dirichlet's conditions if it satisfies the following conditions. First one, the function must be periodic with period and absolute integral over a period. We know periodic function. Absolute integral over a period we know from the previous definitions, right? So f of x satisfies the conditions. It should be a periodic function and absolute integral over a period. Second condition, the function must be piecewise continuous and piecewise differentiable and bounded variation, right? It should be piecewise continuous, piecewise differentiable and bounded variation in any given bounded interval, right? Third one, the function should have a finite number of maxima and minima in any given interval. Definitely finite maxima. So you can take piece, right? Every piece it will get one maximum, one minimum. So it will be a finite only, right? So finite number of maximum and minimum in any interval. So finite Henkel transformation definition. The finite Henkel transformation of a function f of r which satisfies the Dirichlet's condition in the closed interval 0 less than or equal to r less than or equal to a is defined by f bar of pi, which is equal to integral 0 to a r into f of r jn of pi r dr, right? Here we are having the finite limit 0 to a. In the original we are having 0 to infinity, right? That is the difference. So this is the finite Henkel transformation, where pi is the root of the transcendental equation jn of a pi, which is equal to 0, right? And any point of the closed interval 0 less than or equal to r less than or equal to a at which the function f of r is continuous. We have f of r which is equal to 2 by a square summation I f bar of pi jn of r pi divided by jn of a pi the whole square, right? This is the definition of finite Henkel transformation. Thanks.